Join with the same one.
Hello.
Hey guys.
Hi.
Have the participants been let in? Have the participants been let in?
Yeah, I think we have to. Can we change the name, and wait for the speaker, and then let the participant?
All right.
I have to mail the speaker again. I think. Sorry. I think we can. Yes, I think we can. Dan, you're here. We can start allowing the participants, and then we can get the speaker.
The participants are already in. They're coming in.
Yeah, I think they're already in. Thanks. Dear participants, sorry for the delay. We'll be starting in around 3 to 4 minutes. Is Jason in?
Oh. Yes, I'm here, but I can't start video.
Oh, okay. Hi, Jason. Jason, could you rename yourself? I think it's the name is India.
Yeah. All right. Find myself first.
If you go to more and rename.
Just raise my hand, I suppose. Oh.
Oh, okay. Yeah, it's your name is India. Yeah.
I'll just change it.
Panelists, could all of you rename yourself so that we can see? Yeah, okay. I think Jason is renamed. Great.
Yeah, I've named myself.
Yeah, okay. Yeah.
What should I do? I cannot.
Hi, Mark. Yeah.
Hi.
I think your name is named as India NeuroTechX. Could you rename it to your name? So if you click at your name, that you'll find more as an click rename and you can rename.
Yeah, I find it easier to go to the.
Raise your
I'm on my
hands.
phone, so I'm not sure if I have the same options.
Should be able to go to participants and then panelists
Oh.
and then raise your hand, and then it'll make it obvious who you are.
No. Yeah.
Right, I think I can see who you are because your microphone goes.
Okay.
Oh, we're completely sorry for the confusion. There was some issues with the link.
But what did you say, Jason? Go to participants and then?
Panelists, then raise your hand and it'll show you which one you are. And you should be able to click on the name and hit rename and give yourself a name. Or it also says me.
Doesn't show up for me, but
On
I see all you guys, but not myself.
On panelists?
Yeah.
I
Yeah,
can
because
see.
I can see you talk like Jason Parker or MindAffect, but
There. Someone just
Okay.
changed it for me.
Okay.
Yeah, okay, great. Yeah, I think it's changed. I think Suhela has to change. Is it India NeuroTechX? Okay, I think the attendees, the participants.
I'm using my phone and I don't know how to do this from the phone.
Okay, no problem. Yeah, okay. I think Jason Mark is here, so I think with no delay we can start the session. And again, to the Jason Mark, you're fine. You're able to.
I can't start video or share my screen or anything because it's all blocked.
Yeah, me
by the-
neither.
Oh, you're not able to share your screen. Okay.
It's
Oh no.
disabled.
Now, your host has stopped video sharing or screen sharing.
Oh, okay. Understood.
And Mark also needs screen sharing or video streaming.
Yeah,
Yeah.
video is disabled for me now.
Is Brian in? Is Dhanisha, could you sort that out?
Yeah, I made them the co-host, so I think they can share the screens now.
I think Mark is not yet the co-host.
Yeah, that's the second.
Yeah.
Yes, my video now works.
Great. Okay.
Mark
Mine doesn't. Oh,
I made them the co-host. Both
Okay,
Mark-
Mark. Great. Yeah, it has to work now.
you know,
okay, let's change the camera. Then we should be
it's a
good.
nice blank screen.
There we
Okay,
go.
great. Yeah, great. Yeah, I'm sorry. We're sorry for the delay. And yeah, now I think it's all set. No further delays. We can go ahead with the session. So I hand over to Dhanushya to give a brief introduction about NTX India and MindAffect.
So, hi everyone. We're really sorry for the delay, and we welcome you all to NeuroTechX India discussion forum on MindAffect BCI and live demo. We are glad to announce that we will be having a discussion forums on weekly basis regularly, discussing exciting and potential neuroscience and neurotechnologically related quests. And so, a brief introduction about NeuroTechX. NeuroTechX is a non-profit organization whose mission is to facilitate the advancement of neurotechnology by providing key resources and learning opportunities, and by being leaders in local and worldwide technological initiatives. Our three pillars are community, education, and professional development. At NTX India, we envision to advance the progress of neurotechnology in India. So this is just an initiative for that. So and the agenda for today's discussion forum is going to be a speaker introduction, followed by speaker discussion, followed by a question and answer section at the end. And today we have a very special guest with us from MindAffect. So MindAffect works on cutting edge technology of artificial intelligence and neuroscience. They have developed a BCI and demonstrated that it allows logged in patients to interact or communicate by controlling a computer with just brain signals. MindAffect was founded in 2017 as a spin out of the Dundas Institute Brain Computer Interfaces Lab after the team led by Professor Peter Design won the ALS Prize for Life. The company was founded on the ideal of opening up new directions of interaction for everyone by using biosensing technologies, particularly BCI, to allow communication for everyone, no matter what the physical limitations would be. To speed up this mission, MindAffect recently released a core communication BCI technology as open source to the community to allow makers and the patient teams to experiment with BCIs and develop applications fitted to individual users. So now I would pass over the session to Santi to introduce our wonderful speaker of the day. Over to you, Santi.
Hello guys, welcome back. We're meeting you after a long time. So I'll just go ahead quickly. So today we have Jason Fakar, CTO of MindAffect. So I'll just give a small introduction about him. He's a 15-year veteran in the field of communicative BCI interfaces. He started out in machine learning, especially focusing on computer vision, and then migrated to ML and signal processing for BCIs. He was a researcher and a teacher in AI and brain computer interface for 10 years at the Donders Institute for Brain Cognition and Behavior until 2018. So he led a team which won the silver medal in the BCI race at the first cyclothon competition. During this time, as Dhanushya had mentioned, he also co-developed the core technologies, which won the ALS Prize for Life. And this led to the foundation of MindAffect. And then he started to lead the technical team since then. So we also have Mark, a software engineer at the MindAffect. And without further ado, let's get into the interesting event. Over to you, Jason.
Okay. Oh, cool. Thank you very much. Thank you for the invite, and thank you for the very nice introductions. It's always more impressive when you hear someone else say your CV than when you read it yourself. So it's always nice anyway. I didn't actually send you any information about Mark, but Mark is actually a master's student in brain-computer interfaces. He did his thesis project on EMG-based, so muscular-based control for patient applications as well. So he also has a strong background in brain-computer interfaces and general neurotechnologies. What we're going to do today, I guess he's not going to say a huge amount, but you'll see his brain and back of his head a lot as he does little bits and pieces for the live demo. Yeah, and just so you know, he can't really see us, but he can hear us, as you can see. So hopefully this will all work out nicely as a live demo. Okay, yes. So thank you for the invitation. I'm going to start with a little bit of background on what MindAffect is. Then we'll jump into the live demo. And then we'll jump back to a bit of a presentation where basically what I want to show you and what I want to convey is that we have this BCI, it's open source. We'd really love people to try it and just give you a feeling for the types of things that are possible with the technology that we've released as open source. And yeah, try and encourage people to try things. And then for the Q&A discussion session at the end, I mean, yeah, whatever you want to ask, go for it. So with that in mind, I'm going to switch to my presentation. Also, I sent a link for slides out earlier, so I hope they were already shared. So there's a lot of video in the slide. I know videos can sometimes be challenging, so if you have issues with the video stream and things not looking particularly nice, then you can, of course, just click directly on the link in the slides, and then you will get a nicer version of the videos. Okay, so yeah, just an overview of what we're going to talk about. I'm Jason. I'm the lead machine learning architect, the CTO at MindAffect. And I'm going to talk about specifically our open source release, which we call MindAffect BCI, because we couldn't think of a better name. So if anyone has a better name, that would also be useful. And what we want to pitch it as is a high performance BCI for experiment and education. So what I will go through in the next sort of 30 minutes is hopefully show you how those things are true, what high performance means and how it's suitable for experiment and education. And therefore, why I think it's actually a really nice fit for the NeuroTechX style communities, because it tends to be people who are just interested in the technology, want to try things and maybe come up with new business directions and new application domains and ways to use this type of technology. Quick overview of the company. So MindAffect as a company was already mentioned. We were spun out of the Donders to solve this problem. Can you see my mouse cursor? I don't know. But we were spun out of the Donders for this patient support application. So we've been working on brain-computer interfaces for patient applications for 10 years or so. We came up with a nice idea for how to make a super fast, super high performance BCI. We won the ALS Prize for Life. And then we were tasked with transitioning the system that we had from the research lab into something that we could bring to people's homes. And that's what we did. That was one of our primary objectives of the company at the start. And we did that. And so in the end, we delivered a system you can sort of see here, which has a tablet screen, which has a virtual keyboard. So these are the buttons that you can choose from, and you could use that to type or press buttons. And whatever you wanted to use the button presses for would be what you could use the button presses for. We have our user who's wearing a headband. The headband contains the EEG electrodes. And the EEG electrodes, we'll talk about those a little bit later when Mark shows the live demo, are connected to an amplifier box, and that's what makes it all work. And our users that we had found the device really useful. It was very nice. It was, as you can see here, it says the best so far and comfortable. So they found it easy to use. So all the usability aspects associated with the BCI in a home use scenario were problems that we solved at that point in time. So that's where we started in patient support. Last year, as it was already mentioned, we transitioned to an open source, open hardware style platform. And that was prompted by the fact that when we did the actual business analysis of the business case for the number of users who could use our system, not the number of users who could use our system successfully, but the number of users for which our system gave a significant added value above, for example, an eye tracker. The numbers weren't really large enough to have the company as a whole be based on that one market. So we decided to release our hardware and software designs open source. It's been tried to encourage the community as itself to grow and maybe prompt people to try and identify other application domains or other applications. So that's another thing we'd like to promote experimentation so we can identify other things that we can use this technology for. And the last thing we do is we do neurotech consultancy style things. So if you have an interesting application in neurotech and you need someone who knows a lot about biosignals analysis and productizing research things, I mean, that's what we've done. So that's the type of thing that we can do. But that's enough about the company in general. What I wanted to talk more about was the MindAffect BCI. So it's a high performance BCI. There's a lot of buzzwords in here and things about how it works and what it can do and things like that. All of this stuff is online. You can read up about it on the website. So the code itself is hosted on GitHub. There's a GitHub.com MindAffect is where all our code is. And there you can find bits for the designs for the headset. You can find the code for the MindAffect BCI, for the smart keyboard we're going to demo, all these bits and pieces. But I think it's better to show than it is to tell. So we're going to actually, at this point, jump into the show stage. So at that point, I want to hand over to Mark. So I will stop sharing my screen. If I remember how to do that. Yes, I can. And then how can we make Mark's screen be full screen? So it's the primary one for everybody. I don't know actually how to do that. Mark can't do it himself because he's somewhat busy. I don't know Zoom well enough to know how to do that. If I turn off my video, then it automatically will happen?
No, you want Mark's screen to be on the front, like to be
Yes,
seen.
Yeah.
Yeah, just yeah. Tanisha, that's sort that out.
That doesn't help.
I think.
Yeah, you have to put a spotlight.
Yeah.
Yeah, that's perfect. Okay.
Yeah.
Yeah. So as I said, I think it's more compelling if we show you how the system works rather than spending a lot of effort telling you how the system works. So what we're going to do is a live demo of Mark using the system. So Mark's just going to go through and do things, and occasionally I'll ask him to stop and explain what's happening. So Mark, just go for it, and I'll talk over you as we have rehearsed once. Let's see how this goes. Okay, so our system is a BCI, brain-computer interface, which means in our parlance specifically that we are taking signals out of the brain to allow people to communicate. The specific technology we use is a thing called EEG, electroencephalogram, which is measuring voltage differences on the head. We spent a reasonable amount of time in the initial stages of the company trying to get to the point where we had a easy and quick to use EEG system. And in the end, we converged on this particular design, which you can see here on the desk in front of Mark. And this is a water electrode based EEG system. So if Mark holds it up to the screen, you can see the little blue dots. Each of those little blue dots is a sponge, and it has some water in it. So you just saw Mark with a little syringe there putting water in each of those sponges, and essentially he's just making the sponges damp. And he puts it on his head. The strap is Velcro strap. The plastic holder is what you can get the 3D print files for. And we have a design where it also includes designs and parts, materials, and all the lists for all the electrodes and the wires. So you can make these yourselves, or maybe we'll do another Kickstarter and sell them. But essentially you get a headband. It's had 8 electrodes across the back of the head. And each of those has a little bit of water in. And what Mark is doing now essentially is making sure that the water is out of the sponge and bridging across between the scalp, the skin, to the electrode. So essentially the water is the thing that completes the circuit so that we get measurements on the scalp. And the reason we use this particular design is dry electrodes are still somewhat fiddly and annoying to use. The water electrode tends to give us a more reliable signal. And it's really fast to fit. So that was basically, the fitting is now done. So the electrodes themselves are then connected to an amplifier. In this particular design, our system supports a lot of different amplifiers now, because we support anything that's supported by a BrainFlow, and we have a load of other specific drivers, and also anything that can drive an LSL stream. If you know what those things mean, then you know what that means. If you don't, look it up. Basically, any sort of modern amp where if it has an LSL stream, we're supported. If it has a BrainFlow, we're supported. The particular one Mark is using here is an OpenBCI Cyton. So it's from the OpenBCI company. It's an 8-channel amplifier, and yeah, you can see all 8 channels of EEG in front of you. So this is the viewer that's built into our application, and it looks like EEG. If you know what EEG looks like, you go, okay, it looks like EEG. Yay, that's good. Okay then, Mark, I guess we move on to calibration.
Yes.
Okay, so we include a lot of different applications in part of the open source release. We have some standard things, some basic game demos and things like that. The one that we're going to use today is a so-called smart keyboard application, which is for communication. So it includes predictive text and all those sort of cool widgets that are useful for typing and generating text. I have to say that actually this application was developed by a bachelor student team actually in 3 months, going from no BCI knowledge at all to making the whole system. So I think that's a nice example of the system is fairly easy to use. And yeah, so we're doing a brain-computer interface. And there's a few different types of brain-computer interface. The one that we use is one that's based on evoked potentials, which basically means you look at the brain response to a stimulus. And in this case, the stimulus is visual. So this is Mark is doing the calibration stage of the BCI, which is basically where we get example data for this subject on this day of how their brain is responding to the stimulus. And you can see the stimulus here is essentially that the buttons on the screen, you can just see that they're flickering. In real life, they're flickering at 60 hertz. Obviously, on the video stream, that's all massively downsampled, so you can't really see it very easily. But they're sort of flickering on and off at around 60 hertz. And every time they get bright, we get a brain response, we get an example brain response, and that then we feed into our machine learning algorithms to work out what this particular person's brain, how it's responding to the bright and darkness of the stimuli. And here's the calibration stage. And you can see the calibration is fairly simple. Basically, one of the numbers turns green. That's the cue to say, look at this number. You look at it, well, it flashes, we get the brain data, and then that allows us to fit our machine learning models. So then machine learning model happens in the back end. That was the model fitting. It's already done. It was basically the particular algorithm we use is extremely computationally efficient. So it trains in like a fraction of a second, and then we're done. And you'll also note that the total calibration time is about 45 to 50 seconds. So fitting the model to the data to the user is really, really fast. So it's about under a minute to put the cap on, another minute to do the calibration. And then we can jump into actually using it as a BCI. So we have a chat thing, I guess. We've tried to do this before where we actually try and get Mark to answer questions live. Let's see if we want to do that. So I guess in the chat, or Mark, I guess you could start by typing something, but and then if we switch into the chat, then if someone has a question for Mark, then he can try and answer with an emoji. So smiley face, frowny face, yes or no, crying, whatever else. So I don't know if anyone has a question for Mark about using the BCI.
Attendees, could you drop your questions for Mark in chat section if you have any questions? It'd be interesting to see Mark answer.
Yeah, I mean, I can already do one, of course, which is, what's it like to work at MindAffect?
Yeah, I'll post the first question. I'm sorry.
Yay, smiley face. Okay, he had to answer that way, of course. How are you feeling today, Mark? Oh, was that a preemptive answer? Okay, this is always the risk with live demos, damn it. Question mark, okay. You don't know how you're feeling. I guess it's a little bit nervous when it's this difficult. Do you have any more questions? What about the weather today? Do you like the weather today? So no, but it's just probably fair. So you can't see, but it's cloudy and rainy today in the Netherlands, so that makes sense. Oh yes. Oh, so bad it makes you cry, huh? Yeah. So I guess Mark can you switch back to the main keyboard and just type some letters, and then I'll talk through what it looks like. I mean, what's happening on the screen, just so you sort of understand what's happening. Okay, then Mark, just type something, I don't know, whatever you feel like. Just sort of explain what it is that you're seeing. So you can see all these letters on the screen. Each of them are flickering. You can sort of see it a little bit better now. As I said, it's actually much faster than it looks because of the way the video works. But you sort of see each one is flickering in its own different way. And so that flickering is what makes the brain response, and that feeds into our machine learning algorithm. And you can also probably sort of see that every letter has its own pattern of flickering. And because every letter has its own pattern, the brain response is unique for the letter that you're looking at, and that allows us to do this back inversion to work out where you're looking at. I don't know if any of you remember, used to be you had these like laser games with laser pistols back in the day. They actually worked in a really similar way. So if you know how that works, then you can sort of see what we're doing. And you can also see some things that are sort of properties of our BCI. Firstly is that you can sort of, if you watch it, you'll see that some of these times, some of the selections are fast and some of the selections are slow. And that's because behind the scenes, the system is computing the probability of every letter every 10th of a second. And when one gets sufficiently confident, then it does its thing. So we get this variable thing. So for badly performing subjects, it takes a bit longer, but it's all automatic. And for well-performing subjects, then it's really, really fast. And things look a lot nicer. Also, this particular system, the speller system, also has a voice thing, so it can speak the words out. So when Mark's finished typing "Hello NTX India," I guess he'll make it say the words out. But is the speaker loud enough? We'll see. Yeah, and also you can see, of course, that the number of symbols on the screen is quite high. So here we have 30-something symbols. And then, yeah, it does the selections. Also, you can see at the top, it has the predictive text things, which I guess NTX India hasn't been spelled very often, so the predictive text isn't so useful.
Hello, NTX India.
Nice job. Okay, so that was the live demo. And also you get a feeling for the speed of selection and everything else. And you can see there was no cheating involved. Literally, you saw him put the thing on, do the calibration, do the spelling, answer the questions. So that is what we have, how it works. That's what we have in the open source release. And that's exactly the type of thing, if you're interested, you can get the software, get the hardware designs, get to buy an amplifier, and then you can try it yourself. So then I will switch back to sharing my screen. Thank you, Mark. Really good job. I guess you're off the hook for the rest of the day, if you're going to stick around or not. And I'll switch back to me. Give me a second. Two screens at the same because I also have video. So in slides, of course, we have a video recorded previously, but obviously a live demo is more convincing. We should have recorded that. That was actually quite cool. Anyway, sorry, you want to see Mark again? So I hope that that's convinced you that we have this BCI, which is high performance. So it's fast, you can have many outputs, and it can do all sorts of really cool things. But also we want to sort of express that we designed the BCI to make it easy for people just to try things themselves. So you can do all those sorts of other things. So we showed this demo application there that was on like a computer display, of course. So we can do things where instead you can run it on different platforms. So again, I hope the videos work well for you guys. If not, you've got the links so you can play the videos directly yourself. Our system works on the computer display. You already saw that. And sometimes it's faster, sometimes it's slower. I think it was a little bit faster in this demo. But okay, you've seen a computer display, so that's not so interesting. And eventually, I'll skip ahead a little bit. Yeah. And the cheesy music. We can also run on a TV screen. So in this case, this is one of our other employees, Cash, and he's using it on a TV display, as you can see at the other side of the room. So, I mean, both. We can run it on a TV screen or on a local monitor. So that's also cool. So also, we've also tried it actually on the beamer. So if, for example, where you can beam it onto like the side of a wall, and it can be like 16 feet high or meters, whichever unit you're using. Also, of course, tablet screen, no big deal. Runs on a tablet screen, works fine. And also on a phone. So these are just Android smartphones. If you're interested, we have the Android apps. And so you can do it here. And this also is a home automation application. So in this case, the system is hooked up to a home automation system, which means you can do sort of all the device control for these type of patient applications. So if you want to experiment with different types of screens, different screen formats, then yay, no problem. And as I said, we've also done it with the beamer. We've also done some things a little bit more interesting. I'm wondering about, oh yeah, okay. I mean, so you can also, of course, use the BCI for lots of different applications. So if you're in, yeah. So there's a load of different things we tried. So this is one thing. We have, in this case, a Lego robot, which has lasers. And the lasers are projecting into the world, that sort of bright, dark pattern. I'm going to just show it again. And that allows you to be able to control the robot. In this case, it's a Lego robot by using the BCI. So you just look at the thing and they move in the direction of the little arrow. Here we have a different type of robot. This is a Lego. This is not a Lego Sphero, it's a Sphero. It's being controlled by the tablet screen with the BCI. So you can hook up to all sorts of interesting devices. The next one's more of a fun one. So in this case, if you know there's a fairground thing where you throw balls at tins and you try and knock them over and try and knock them all down. Here we're doing that with brain signals. Basically, you can again see that I'm going to find it back. Each of the cans is flashing because it's got a light beamed on it. And that allows us to do the code to select which one you try and knock down. And then we have a little air blower that blows the cans down. We can, of course, have it that you can control a TV. Yeah, TV control, why not? So if you're feeling super lazy and you don't even want to reach for the remote, you can just use it with the brain signals directly and control. In this case, I think it's Apple TV, controlling Apple TV. Yeah. Or you can use it for controlling the lights in your house. I mean, so but basically the point is that in all these cases, we have a little Python backend. The Python backend means you can connect something coming from the BCI to whatever output you want to do. And just go for it, whatever you feel like. Last thing I want to talk about is, yeah, you can also do more interesting things with it. So obviously, we're all of an age where video games are a thing. So we thought, of course, why not do brain control video games? None of us are game designers. Our games are crap and look horrible, but you can do something as simple as tic-tac-toe, which is sort of obvious. Here's tic-tac-toe on the TV screen. against the computer, and our computer is really stupid, so you win. Yay. We also have Snake, of course. I'm of the age where Snake was a thing. It was really big in the old big Nokia phones. So this is brain-controlled Snake. Again, this is on the TV with our other employee Cash. We can also, of course, do Space Invaders, which I have to say is even a bit old for me, since it's just before I was around. In this case, though, is also what's interesting to see, and in this game as well, this is a first-person shooter with a brain one-shot kill. So basically, if I pause this a second. Too slow. No. Oh, sorry, I messed up. In that game, I just wanted to mention that the, oh, no, wrong one. The, okay, buff. Let's not worry about that. Let's move on. But anyway, I wanted to say that in that first-person shooter and also in the Space Invaders game, one of the nice things about our BCIs is very robust to interference, so from other activities. So in both of those games, you could see that the person for the Space Invaders was tilting the screen in order to move the player at the bottom to dodge the incoming missiles, but still able to select the aliens at the top with the BCI. So having movement and BCI control simultaneously is no big deal. And also in the first-person shooter, it was the same idea. So you had general keyboard controls to run around in the world, and then the BCI was able to do like a special move, a special like one-shot kill brain shot to wipe out enemies in one go. So that was sort of the paradigm we were going for there. But also, I just want to say, the game design thing is something we think could be really cool and really interesting. It's not something we as a team have the skills for. So if someone wants to go down that route, we'd be really happy to support them, particularly if they knew something about game design so it could really make a cool and compelling game. That would also be really cool and really fun. Okay, so we've covered we covered part of experimentation in terms of outputs and applications. The other thing you can think of in terms of experimentation is in classic BCI styles. I mean, other types of BCI. So we've all talked about all the stuff I've shown you so far as being our particular type of BCI, which is a thing called a code visual evoked potential. But of course, there are other BCI paradigms. So one of the classic ones is the row column speller. So here's a row column speller running on our BCI. And basically, it just works. We just, there's a few parameter settings and we have instructions on how to do this. You tweak a few parameter settings to say the brain response is slightly different, it's a different type of response. And there you go for a row column speller. And actually what we were slightly surprised by is the row column spellers are normally quite slow, but it's actually not that bad here. It's not that much slower than our particular CVEP. Another thing from a few years ago is a thing called the faces speller, which uses faces because they activate a slightly different brain region. So in theory, that can give you a better response. So this is a row column faces speller again. Yeah, okay. You want to experiment with the different BCI paradigm? Go for it. Just build it and try it. And it should just work. And the last one I want to show here is in terms of visual style BCIs, a classic alternative to the code visual evoked potentials is thing called steady state visual evoked potentials, which is where in this case, each of these numbers is flickering a slightly different frequency. So one's flickering at a higher frequency and the other lower, and we can use that as well. So in this case, we're using the steady state visual evoked potentials and away it goes. And again, basically, this is with a very minimal amount of change to the BCI code. So you just change what the stimuli look like and you change a couple of the analysis parameters and away you go. And you get all the advantages in terms of the probabilistic outputs and the adaptive stopping and having multiple outputs. All that stuff just works out of the box. Also, we have non-visual demos where instead of using visual inputs, we can use, for example, auditory inputs. So you have beep streams or tactile inputs where you have little vibrators on your fingers and doing streams of pulses on those. Again, fundamentally from the algorithmic side, the algorithm doesn't care if the stimulus is coming from ears or touch or wherever, it just does the analysis. So those are all doable and workable. We don't have any nice videos of those yet, but maybe later. Yeah, so as I said, so we have this MindAffect BCI, high performance BCI for experimentation. So you can experiment with output devices or BCI types and those types of things. It's very good for educational, so learning about BCIs or neuroscience or AI. And we tried to make that as easy as possible in a few different directions. One of which is that we include out of the box again all sorts of interesting stuff in terms of visualizations of what the actual BCI is doing behind the scenes. So this is one style of visualization that we have, which is where it shows you what the fitted model looks like live as the system is running. So this is a real-time run. So this is literally after whatever this is, like 10 seconds of data. And if I just pause it here, or maybe not here, you have to go away. Then what you can see is this is a visual evoked potential style system. So this is a topographic thing of the back of the head. You can see our headband with the electrodes running from left to right on this visual cortex. And after about 20 seconds of stimulation, you can see that there's a response at the back of the head. And there's two types of events. I didn't really talk about what an event is, but you can talk about that in discussion if you want. And we can see that we get some big difference in the response at around 200 to 300 milliseconds, which is actually what we expect for this type of BCI. We actually expect it to be like an N1, N2 complex, so it's 100 milliseconds, but because of the way our stimulus run, there's 100 milliseconds lag built into the system. So actually everything shifts out to about 200. And that's super useful just for if you want to understand what is happening in the brain when the stimulus is happening, because you get these really nice plots. And after a while, you can sort of see, look, what we see is a thing at the back of the head with a massive response at around 200 milliseconds. So we're responding to stimulus at 200 milliseconds. You can also end up finding multiple components. For other types of BCIs, you might expect to get 2 components. For example, with a P3, this is sped up, by the way, at 64 times. For a P300 style BCI, particularly a visual one, what you actually expect to see is 2 parts to the response. You'll get a visual part, which is just to do with the stimuli, and you will get a so-called P300, which is to do with the fact that you recognize the target non-target distinction. So again, this is running the analysis. Take a step back. Too slow. And after the end of the analysis, again, you actually sort of see what you sort of expect. You have one component, which is only at the very back of the head, which is the visual part. And in this case, you sort of see that the main response is here. It's around 200 to 300. And then you get a secondary response, which is slightly further forward on the head, so more in parietal cortex, if you know what those things mean. Anyway, it's slightly further forward on the head, and it's a little bit later. And a little bit sort of broader in time, sort of last 200 milliseconds, which is more a classical P300 style response. So again, you get this sort of automatically when you just run the analysis, and that there then leads into the fact, okay, what are these things? Oh, okay, one is a visual thing, so that's the early visual response, and this is the P3 response. So that in itself is super useful just for educational style purposes. We also, for BCI style applications, we have some live viewers of the output of the BCI. So in this case, you can see over time what the BCI thinks in terms of, in this case, there are 34 options on the screen. I don't actually know what they are, but you can sort of see after about 1 second, one of them starts to pop out, and then it takes a little bit more time to rise up to hit threshold. And here you have the time course of it, and you can sort of see it, one pops out of the background and eventually rises up to the point where it hits a probability of being selected. So you can sort of get a feeling for what's happening in the BCI behind the scenes. Go away. The other part we have in terms of like teaching for brain-computer interfaces specifically is on our Read the Docs page. We have a lot of different tutorials of how to do things, how to build your own BCI, how to build your own stimuli, how to build your own output, how to implement a different class of BCIs, whether you do the P3 or the SSBP or blah, 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 blah. A lot of stuff there. It's really cool. And the last thing that we have is we also have, for people who are interested, not so much in the BCI, but in the machine learning, we have uploaded some example data sets to a Kaggle competition page. It's not a live competition. It's just somewhere where the data sets are available, so you can run all your analysis on the cloud and exploit the Google free servers in Colab. The data sets are already there. We'll add more to them as time goes on. And that's also somewhere where we think it would be really nice if the community wanted to get into this and start actually allow the data set to grow over time and include more different interesting paradigms and things. But anyway, the data sets are there. We have example notebooks for how to run an analysis of these data sets, and then you can have at it to see if you can make a better learning algorithm. And we would love people to do that, because if we can make the BCI performance better, then we can maybe open up new application domains and also just help people who are currently using the system. So if you're interested in machine learning, then you can look at the example data sets. So that was actually the end of my presentation. I hope I'm roughly on time. And yeah, I would just like to respond, repeat. So the MindAffect BCI is there. It's open source, open hardware. So all the bits are there. If you want to try it, you can try it. If you have an EEG system and a headset, then you can just jump straight in. If you don't, you have all the instructions for what you need to do it. And we really would just love to have more users. We'd love to get your feedback and experiences and bug reports. More bug reports are always a good thing, even though they never feel like it at the time. We're also interested for developers and researchers. Can you improve the machine learning part? Do you want to use it for end user studies, investigations in different populations, whatever? It's open source, do whatever you want. One caveat I didn't mention, of course, is that the open source license is non-commercial. If you want to go commercial, then you have to come back to talk to us. But okay, we can talk about that maybe later. Another thing is, if you want to build an EEG device, we would love to support as many devices as possible. So anyone, if you have an EEG device that we currently don't support, then we'd love to be able to support it. If you want to build a EEG device, we would love to talk to you. Because that's something where we feel as a company we have a slight hole, is that we don't have our own EEG hardware, but we are a software company, so that's sort of where we focused. Yeah, and also if you're more interested in the commercial side, as a company, we're looking for partners in all other parts of the world, India as well, and particularly in the education and gaming sectors, which I already mentioned, because I think those are actually two sectors where there's some low-hanging fruit, as they say, where there's clear things that we could do to actually sort of have an actual market relatively rapidly in those sectors. So with that, I would like to, just quickly mention our team. You already saw Mark, there's me. You already saw Cash in the videos and our commercial partners. And yeah, you also have all the videos, and then I think I will stop. And yeah. Thank you all for listening, and I guess it's QA time. Yes.
So this was such an awesome session, and I'm really sure that the panelists and also the attendees were so very excited. We could look at the comments in the chat section. They were all like, "This is awesome. This is cool. Thank you for all the coolness and awesomeness that you shared with us, Jason. It was really an insightful session today." So moving on to the question and answer session, we have the first question from Deepak Mevada. I would request Deepak to unmute yourself and ask the question yourself.
Yeah, hello. Can you hear me? Yeah. Hello. So my question is like, what is the technology behind the application, and is it publicly available? Like, can I read about it? Regarding what signal acquisition strategy you are using and which classification algorithm you are using?
Yep. I mean, so at one level, you can do this because the code's there. I mean, literally the code that we used for all those demos is there. It's all Python. It's all there. There's minimum dependencies. I think it depends on like 2 or 3 different libraries. Also, if you look on the Read the Docs page, there's a load of stuff on there. I think there's a full reference list. If there's not, then bug me about it, and I'll make sure we put the reference list up. So it's based on some academic papers that we published back in 2014 called Reconvolution with Noise Codes. But if you search for my name in Google Scholar, you'll see it somewhere in there. But the papers are there, they're public, the code is there, it's public. Some of the core algorithms are also patented, so you can find the patents, and that's partly why we have this commercial, non-commercial thing, but all the code and the algorithms are there for sure, and they're open source, as is the papers that describe the algorithms in the core. I don't know if you want to talk about actually like an overview of how the algorithms work or not, or just talk about where you can get the technical details that you're interested in? And okay, really briefly, the brain response that we use is a visual evoked potential. So it's nothing to do with motor imagery, nothing to do with cognitive load. It's just to do with, did your brain, or your visual cortex specifically, see a change in the visual inputs? And that evokes a potential, and then we do everything based on that. So everything gets backtracked to, was there a change in the external world? Did you see it in the brain? And then if you did, from what you saw in the brain, which of the external changes does it match most closely to?
Could you please share the link of research related to research paper, or like the name of the person, so that I can search on the net?
Yeah. Give me a second or so, and I'll find the link. Or I don't know if Mark's still
Thank you.
around. If you can do that in the parallel. Yeah. Okay. Yeah. I can. Give me a second. I'm just googling it quickly.
I've shared your Google Scholar profile in the chat.
Yep. So the main original paper is this +1 paper. I can just put it in the chat. Okay. Yeah. As I said, yeah, it's a fair point. Actually, we should have a references list on the read the docs.
Okay. I think there was another question from Suraj and Shane. Could you kindly unmute yourself, any of you, and ask your question, Jason?
Hello. Yeah, my question was, how many words per minute can you type with this device?
Oh, okay. So that's obviously there's actually some extent there's a potential trick question in there. So I'm going to answer it in two stages. Firstly is the way the system works is not really about words, it's about selections. So how many selections can you make in a minute? And that comes down to, it's actually a combination of how many options are you choosing from, and how long does it take to choose each option. But in a general sense, for a sensible full keyboard, which is about 30 options, the selection time is sort of 2 seconds to 5 seconds, depending on the user. So some actually, and sort of for most users, you can actually get some users that are down to about 1 second, but on average is sort of between 2 and 5. So for the demo we did with Mark, I think it was today, it was running somewhere around 2.5 to 3. That's sort of what it felt like. Maybe it was a little bit quicker. And that's in terms of number of selections that you can make. So with a normal keyboard, without any sort of fancy modeling and language modeling and predictive text like you have on like a phone keyboard, that would mean that you can do, if you tweak all the other parameters optimally, say 20 characters a minute, and normally we define a word as 4 characters, so then you would wrap that down to about 5 words a minute. Of course, that's if you make things hard for yourself. If you add predictive text on it, and particularly predictive words and things, then the number of words you could get out in those 20 selections or so could actually be way, way, way higher than that. So that's why it's sort of, the words per minute thing is a little bit different. But in terms of selections per minute, it's roughly sort of 2 to 3 seconds of selection. So you work out to be 20-ish.
Right. I think there was another question from Shane. Shane, could you unmute yourself and get your question? Shane, you're there? Okay, maybe I can read his questions. So his question was about, so I saw Mark moving their heads towards the option they want to choose. So do you think the models might just learn these patterns? I mean, these movements can interrupt with the data and the models can, decode this movement? That was a question.
Okay, yeah, it's a fair question. It's not actually the question we normally get, but okay. So the electrodes are super sensitive. E.g. electrodes are sensitive to everything. So they do pick up something associated with the head movement. But that's not at all a problem with the system. Mainly because one of the first things that we do in the pre-processing is we filter everything below 5 hertz. So actually that head movement is definitely not happening faster than an oscillation at 1/5 of a second. I mean, it's just totally not happening. So it's removed by our pre-processing. So it can't even leak into the data that we're analyzing. So in that sense, we're not, it's definitely nothing to do with head movement itself. There's a secondary question that comes up quite frequently associated with that, which is it to do with eye movements? And in that case, actually, the answer is a little bit more subtle of saying that actually, it's not, again, to do with eye movements in themselves, because they are very slow and they don't have a big effect and they would be filtered out by our filters. But one thing that the performance of this particular class of BCIs does rely on is the fact that your eyes are pointed predominantly at one of the targets, one of the buttons. And what that means is, because of the way the brain and the visual system work, most of your brain is actually processing that particular target, and that means most of a large fraction of the visual cortex is activated by that particular target, because of the fact that you can point your eyes at the target. So if you weren't able to move your eyes, the response would be much weaker, and the BCI performance would be much worse. So this is a big thing in the field of BCIs in general, is about gaze independence versus gaze dependence. And to be very honest, this particular BCI is pretty heavily gaze dependent. And it can work without gaze, but the performance is a lot worse. So the head movements themselves, no. The eye movements, yes. But not the movements themselves, but the fact that if you're looking at a particular one, you get an enhanced response to the thing you're looking at. And then there's a big debate about, is that actually it's a gaze-dependent BCI. It's clearly using the brain responses. It's using the fact that the brain is processing the stimuli, but it's mediated indirectly through muscle control of the eyes.
Yes, yeah. So I have one question follow up to that. So what are the electrodes? You mentioned it as a sponge. So what is the electrode that you're using, and what is it compared? So when we compare this with other hardware devices which has dry electrodes and BCI applications, what is the comparison?
Yeah, so we did actually internally, we did a lot of study. We did a lot of empirical comparison of different dry electrode types. So we compared 4 or 5 different dry electrode types. And these water electrodes. So the water electrodes, the ones that we use in this demo are ones that are manufactured by a company called TMSI, which is Twente Medical Systems Incorporated, which is based in the Netherlands as well. But the idea of a water electrode, EGI made a set like that. Brain Products have a set like that. So they're essentially, it's not a particularly unique design. And also we have, as I said, we have this open hardware design where it's not based on those electrodes. Basically, it's a standard EEG electrode with a silver chloride sintered thingy, electrode tip, and then a sponge with tap water. So the old emotives, if you remember back from the emotive epochs, they used a saltwater solution with a gold cup. These are a silver chloride with tap water. And as I said, when we did all our testing, what we found was that dry electrodes can be good, but there's 2 big caveats. Caveat number 1 is that there also can be really bad, and it can be a bit awkward to get them to the point where you get a reliably good signal. And caveat number 2 with the dry is the performance is very sensitive to the amount of pressure you put on the head. And that, for any sort of long-term usage, really kills it. I mean, if you were thinking of patient application where you want the person to wear this system for 5 hours, it's just a complete no-go. It just doesn't really work at all. That I have to say was when we did this testing like 2.5 to 3 years ago. I know dry electrodes have moved on since then. Maybe now with the newer materials that are more flexible and softer, if we redid that test, we would come to a different conclusion. But the conclusion we came to back then was dry for long-term use for patient applications wasn't really where we wanted it to be in terms of reliability and comfort. Whereas the water system, comfort-wise, it's fine, and reliability is actually, it's a lot easier to use than the dry sets. And of course, compared to gel is always going to be the gold standard, and it's always going to be better, but gel is so annoying to use that we don't even talk about it.
Sure, yes. Do we have any other questions?
Yeah, I have a question. Karthik. So Jason, so there was a calibration process before the entire thing. So can you explain in brief what exactly is the machine learning model trying to learn, and a small brief on the concepts?
Yeah, okay. Maybe I could, is it worth showing the video again? I mean, okay, I just quickly share my screen. So I know Mark is gone, but I can, fortunately, I have video. Oh, yeah, wrong one, wrong tab. You can still see this, the right tab, I hope.
Oh, the screen is blank now.
Oh, the screen is blank now. Okay, yeah, that happens sometimes. Let me just fix that. Let's get the right tab always. Yes. Now?
Yes, now the screen is.
So if I play, this is like a pre-recorded one, as I said, from from a while ago. Let me just skip to the calibration. It's about a minute and a half. Yeah. So I guess you can see here what's going on. So what is happening is, if you look at the individual character, what you can see is it's flickering really, really fast. As I said, it's happening at about 60 hertz. And what that means is that essentially, because Mark is looking at one of these targets, his gaze is fixed on one of those targets, that bright dark sequence is processed by the eyes. It goes through the optic nerve and into the early parts of the visual cortex. And then the visual cortex responds to those brightness changes. And what you find from, if you look into the neuroscience literature, but also what we find empirically, is that basically what the brain is responding to is when the brightness changes suddenly. So what you see is you get a response to when it goes from a dark state to a bright state, and you get another response when it goes from a bright state back to a dark state. And that is what we ask the system behind the scenes to model. So it tries to fit a model to say, how is the brain responding when what it's looking at gets bright? And how is the brain responding when what it's looking at gets dark? So that's the core model. So we model it as there's two types of events coming into the brain, like dark to bright and bright to dark. At each of those events, there has a particular response shape, which is like an ERP. And then it happens for a particular location in the brain, so a particular source, so one particular brain location. And those are basically the constraints that we put on the model, and then we let the model fit it. And I saw one of the questions earlier was, I mean, what type of model are we using? But in the core algorithm we use is based on a thing called canonical correlation analysis, which is just a linear model fitting system, which is why the fitting time is really, really fast. But the reason that it actually works really, really well is because the assumptions of that model, like linearity, that the brain responds to these bright, dark, dark, bright transitions with just generating a response, that there's a single neural source that generates it. All those constraints we put on the model mean the model fits the data really, really well. Doesn't need a lot of data to fit because there's not that many parameters. I think in the end, this model has like less than 100 parameters. So we can fit it really fast. And so we can fit it really fast in terms of not needing much data. It's very machine learning efficient. And we can fit it really fast in terms of not needing much computation. So we can actually do the model fitting really fast. And yeah, I hope that answers your question, maybe in too much detail. Anyway, what else? Yeah.
Jason, we have just one question from the attendee. Are you free like for 5 minutes? Is it okay if you could ask another question?
Yeah, sure. I have a little bit more time, yeah.
So the question posed to you is there any particular frequency we are using in these models?
Any particular frequency? So this is one of the, maybe a misunderstanding about the technology. We use a thing called a code visual evoked potential. And what that means, all that means is basically when you can see it flicker, and it's hard to show in these videos, but if you look at the stimuli in detail, it's not periodic. It's not like it goes on, off, on, off, on, off, on, off. It goes on, off, 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 on, off, off, off in a random sequence. So essentially you get sort of random sequences of ons and offs. So it's not any particular frequency. And that's this property called spread spectrum or noise coding is one of the things that we use. So for this particular design, there isn't a particular stimulus frequency that we use, apart from the display rate of 60 hertz. So if you look at our the way that the flickers happen, what you'll see is they have bits down at 10 hertz and bits up at 60 hertz and everything in between. I showed in one of the earlier videos that the same technique works for so-called steady state visual evoked potentials. In that case, then yes, we do have particular frequencies of oscillation because we are using the ones that work the best. And in that case, I think the frequency we're using are 7.5, 10, 12.5, 17, 20 something. But you could have a look at the code and you can see what's going on there. So the basic answer is no, unless you use an SSVP analysis, in which case it's using the frequencies asked for.
I hope that answered his question. So
yeah, I mean, if it doesn't, then just reach out. So my email is Jason at MindAffect. You can always just contact me by email.
Right. Yeah. Okay. So I think we've come to the end of the session. So first of all, thank you, Jason and Mark, for giving such a wonderful presentation, and thank you for patiently answering all the questions. And again, we apologize for the delay because there were some issues with the link. Hopefully this doesn't happen the next time. So I have some good news for our NTX India members. One thing is, I hope all of you know NTX India started in August. In January, we reached the 600 plus mark in Meetup page. So there was a huge interest after the NTX India's webinar on November. So, and a lot of people are becoming interested in neurotechnology. I spoke to a lot of people in India recently. So it's a good sign. So what we've done, we have huge plans for NTX India. This year, 2021, we're planning for a lot of events. So one thing is we'll be having weekly discussion forum, which means every week we'll be having discussion forum where we'll be hosting Indian speakers, professors, researchers, entrepreneurs, and also people who are interested in sharing their neurotech knowledge. And we're also working with closely working with professors at IIT and a lot of other universities in order to build a very huge network of Indian neurotechnology. And let's join together on this mission to build some neurotechnology in India and from India for the world. So we'll be having around 40 forums, discussion forums in this year, along with 2 large webinars, which we'll be hosting, which we'll be hopefully conducting on around June to July, and also around November, which are very, 2 or 3 day conferences with a lot of speakers and interesting. So there are top companies like, so we actually spoke to Jason, MindAffect last week, and he was very interested to get to India and present this. He was so kind for that. And also we have a lot of people interested to get into the Indian neurotech ecosystem and would like to collaborate with us in order to build neurotechnology in India and also for the world. So hopefully, I've also shared the NeuroTechX India social handles in the chat box. Kindly join our social handles and also kindly use this hashtag for any neurotech related posts that you put it on your social media, hashtag neurotech for India. You're going to work with a lot of people and make this hashtag really popular in Indian ecosystem. So thank you so much for all of you for attending this forum. Hope to see you in the next forum, and especially thank you, Jason and Mark, for your wonderful time, and hope we'll work closely with you. The Indian ecosystem will work closely with you and do some wonders in the field of neurotechnology. Thank you so much.
Yeah, thank you very much for the invitation. It was really nice. It was really nice to get lots of cool and excited questions. So that's always nice to get nice feedback.
Yeah, okay. So this recording will be also streamed in YouTube. You can also watch it in YouTube or ask your friends if they haven't seen it. So yeah, thank you so much, all the attendees and the speakers. Thank you, Jason. Thank you, Mark. Yeah.
Thanks. Bye.
Okay. Yeah, bye. Yeah. I think we can leave the session, right? See you on next Saturday at between 7 to 8. We have one more interesting speaker. Yeah, thank you.